Finally, in discussing amino acids, I've touched upon this a couple of times. Amino acids are, of course, all chiral, with the exception of glycine. Let's just have a recap on that because it has been a long time since we introduced the idea of chirality and enantiomers. We have any situation in which a carbon has got 4 different groups around it. That carbon is stereogenic, it is chiral. What that means is that in a very simple sense, when you've just got the one chiral carbon in a molecule, that the mirror image of this molecule is non-superimposable with it. Now, the physical manifestation of that is that these are optically active. They rotate plane polarized light, which, if you remember, is just light that instead of approaching it from all different angles is just coming at it in one direction. One enantiomer rotates the light one direction, the other enantiomer rotates the light the other direction. What is really important in terms of amino acids and biological stuff is that you're not rotating a whole amount of light in the body, but because these are different molecules, one enantiomer will fit into a particular hole in a molecule that the other enantiomer won't fit into that hole. Enantiomers have the same chemistry as far as we're concerned as organic chemists because they have the same functional groups in the same relative position to each other. However, when we're thinking about in terms of biological activity, the biological activity of different enantiomers can be grossly and dramatically different. Now, I've got in here, just because it was in the original slide that I did for amino acids, and I see no reason not to reinforce it, just the emphasis of a non-superimposable mirror image. If we draw the 3-dimensional version of this molecule here, so there's the W and the Y going away from us, the X and the Z groups coming out at us, and then I construct its mirror image, like that. So let's make sure we see that this is indeed the mirror image through that plane coming out at us, the X and the X, the Y, the Z and the Z both coming out at us, but again you can see the mirror images of them. Because the mirror plane is parallel to the YCW direction there, then those don't change in the mirror plane, so W is still going away from us up the top, Y going away for us down at the bottom. Now, if I look at it from this perspective, and I see that if I was to pick this molecule up and try and pop it on that one, well, then the Y going away and the Y going away match up, the W going away and the W going away match up. But if I just pick it up and pop it on there, the X on this one would be mapping up with the Z there, and the Z here would be mapping up with the X there. They're non-superimposable. How about if I take this and I rotate it by 180 degrees. So there we are, now that's rotated by 180 degrees. So now instead of the Z being on the right, it's on the left. Instead of the X being on the left, it's on the right. Instead of the Y being on the bottom here, it's on the top. Instead of the W being on the top here, it's on the bottom. So this is that molecule just rotated by 180 degrees. Now if we compare these two, we can see that the Z's match, the X's match, but now the Y's and the W's do not match up. So this molecule here, the mirror image of this molecule, is not the same molecule. It's non-superimposable. It's going to have the same reactivity chemistry, but it's a geometric or a stereoisomer. It is a different molecule. Now, if we think about all the amino acids, of course, as long as R is not H, this carbon has got 1, 2, 3, 4 different groups on it. So that means that it is chiral, it is stereogenic, it has a non-superimposable mirror image. And it's interesting that all amino acids in nature, the important amino acids, all have the same fundamental structure. And that is that if you take them and you draw them so that the hydrogen is coming out at us and the acid group is going away from us, well then the R is always, always, always on the right, and the NH2 is always, always on the left. Every single one of the important amino acids has this structure here. Okay, now I draw it like this because there's a nice little mnemonic the biochemists have come up with to help you remember the structure, and that is corn. Okay, so if we draw it so the hydrogen's coming out at us, the CO from the acid group going round to the clockwise to R, going round clockwise to the N. Okay, so every single important amino acid has this structure. Every single important amino acid is an L. In other words, if you just take the amino acid that's important, the enantiomer that's important, and you rotate light on it, it rotates light to the left. Okay. Now, of course, L and D are associated with the rotation of light. You can't just look at a molecule and say, oh, it's L or it's D. What you can do is you can look at a molecule and you can say it's S or R. Now, if we look at this way I've depicted the molecule here and go back to our SR determinations, okay, hydrogen coming out at us, which means that it's flipped on the rules, okay, but in terms of priority, the NH2's got a nitrogen, the C here goes to 2 oxygens, and this R group is almost always a carbon going off to a bunch of hydrogens and another carbon. Okay, and so priority wise, nitrogen, then the acid group and the R. So as long as R is in that, as long as R is the third priority group, when we go round here in this corn structure, we go 1, 2, 3 in terms of priority, we're going clockwise. And so, of course, because the hydrogen's coming out at us, going clockwise means that it is the S enantiomer. Now, I said all but cysteine are that. Well, what's cysteine? Cysteine is where the R group is CH2S. You've got an S on it, and of course S is bigger than all these others. So the nitrogen is still the top priority, okay, but then instead of the C with 2 oxygens going, we get the C with an S, so therefore the R is the second priority and the acid group is the third priority. So we go 1, 2, 3, where R is cysteine, so of course we're going anti-clockwise here because the hydrogen is coming out at us, the cysteine is going to be R. So all amino acids rotate light to the left, okay, all the important amino acids, the enantiomer that we have rotates light to the right to the left. All amino acids except cysteine that are of interest, the particular enantiomers that are interested are S, but cysteine is higher priority of the R group than it would ordinarily be, which turns it from S to R. Hope that wasn't too confusing, and we will move on in the next movies, stopping thinking about individual amino acids and slapping them together to make peptides.